So in this video lecture, we are going to discuss about AC voltage controller, right? With different types of loads, R load and RL load, that is resistive load and resistive inductive load. So now you can see the aim of this particular test is to conduct and understand single phase AC voltage controller. The name itself suggesting that it is controlling the voltage only. It is converting AC into AC with variation in the voltage across the load, which is AC voltage. So in order to perform this AC to AC conversion with variation in voltage, we require these parameters. First one is AC voltage controller kit. People can see this AC voltage controller kit, right? Which consists of two SCRs, SCR1 and SCR2. You can also get voltage controller across the load with the help of track also, right? But we use two thyristors which are connected in anti-parallel. I will show you the circuit configuration also, right? Then to see the waveforms across the load, like voltage and current, we need CRO with differential mode. Now you can see this is not CRO, it is called a DSO, digital oscilloscope, where you can see your response. And we require resistive and inductive load. Now here you can see this is resistance. This is the inductive loading. You can see different values, 0 millihenry, 25 millihenry, 50, 100 and 150 millihenry. So depending upon our requirement, you can put in between 0 and 25 or 0 and 50 millihenry. Right, and to measure the voltage across the load or current, we need some multimeter also. So now this is what our multimeter, where you can measure the voltage. CRO will display the voltage waveform and current waveforms, but it will measure the voltage magnitude. And you require some probes and patch cards to connect the circuit configuration. So let us see the circuit configuration of AC voltage controller. Here you can see the AC voltage controller circuit. So this consists of two thyristors, SCR1 and SCR2, which are connected in anti-parallel. Right, and the 230 volts 50 hertz AC supply is being stepped down to some 24 volts. If you connect here and here, you can get 48 volts. If you connect between 0 and 24, or this 24 and 0, you will get only 24 volts, right? Which is a AC 24 volts, and this 24 volts can be converted into variable voltage here. So this load can be a resistive load, it can be a resistive inductive load. Here you can see the inductance and the resistance, they are connected in series. So in place of this terminal A and B, you can connect a load here, right? And these are the expected waveforms you will get. So here you can see it is converting AC, is the AC with 50 Hz frequency. It is converting this fixed AC to a variable AC here. So depending upon the firing instant, you can get even you can get full voltage across the load if you fire at alpha equals 0. If you fire at alpha equal 90 degrees, you will get half of the input voltage. If you fire at 180 degrees, you will get 0 voltage across the load. Right? You can also see the voltage across thyristor T1, SCR1, SCR2. And this is for resistive load, right? Where you cannot get, you cannot see the negative peaks and positive peaks. But in case of RL load, you can see the peaks here. Okay, that's the major difference between resistive load and inductive load. So this is with the inductive load, right? So due to this one, there is a reduction in the net voltage across the load because the particular cycle, it will be getting reduced due to presence of the inductance in the load. right? Now, these are the procedures you need to follow to complete this test. We can see, first of all, make the connections as per the circuit diagram. Circuit diagram is given to you, right? We'll show you the when you come to the college. But here you can see two thyristors which are connected anti-parallel, and these two thyristors are connected in between the load and source. Now here you can see the same circuit you can see here. It is a transformer, it is a step down transformer, and this is also used for isolation purpose, right? So now you can see, if you connect in between these 2 points, you will get 48 volts. You have connected between 0 and 24 means you will get 24 volts across the load. If I find that alpha equals 0, and I have connected two thyristors here which are in anti-parallel. You can see anode is connected to cathode, cathode is connected to anode, right? You can see fuse also here. If the particular device is damaged, right, you can see whether fuse is blown off or not, right? And you can also see the firing angle here. You can see firing angle knob here, and with the help of this firing angle knob, you can vary the voltage. So let us see, now you can see the waveform as well as the voltage magnitude, and the firing angle is at 0 degrees, right? So now if I increase the firing angle, there is a reduction in the net voltage. It is of 14.8 volts. Now if I stop this one, now you can see there is a reduction in the net area, so that you can see the RMS output voltage is getting reduced. So now here you can see the positive peaks and negative peaks. And I told you that this is due to presence of inductor. So if I short the inductor, now the load is RL load. Now you can see they are connected in series, right? So it is connected to this point, and here you can see the voltage across the load. Now if I short this one, so there is no effect of the load inductance here. Now you can see it is pure a sine wave kind of voltage. Now you can see if I increase the firing angle, there is a reduction in the voltage. And you can also see the waveform, right? And this is at 180 degrees. Even you can see here, this knob is at 180 degrees now. We can see white mark here, which is at 180 degrees. Now, if I decrease the firing angle, there is an increment in the voltage. You can see the wave shape also, which is increasing now, right? So at different values of firing angle, we can get different values of RMS voltage across the load. And if alpha equal to 0 degrees, you can see almost 22 volts, 22, 23 volts, which is same as the input voltage. If you uh, consider the drop across the devices, there are two devices, and voltage across each device is almost 1 volts. So 1 plus 1, 2 volts, and plus 22 volts. Here you can see the 24 volts is the input voltage, whereas the output voltage is only 22 volts. There is a drop across the devices because they are made up of semiconductor material. So there should be some internal impedance, internal resistance, we can say, and due to presence of this internal resistance, we'll get some drop across them, right? So now you can plot the waveform easily, and different values of firing angle. Now let us adjust this to 30 degrees. Now it is approximately 30 degrees. This is for R load we are discussing about, right? 40.3. Similarly, at approximately 60 degrees, which is 15.4, approximately 90 degrees, 12.2 volts. At 120 degrees approximately, you can get 8 volts, and you can see the waveform as well. Similarly, at 150 degrees, it is around 4.1 volts. At 180 degrees, you will get 0 volts. Both you can see voltage magnitude as well as the waveform, right? The same thing you can achieve for the resistive load, resistive and inductive load, where here you can see I have short circuited these two terminals. So even though I have connected R and L, they are in series. Due to this short circuit terminal, there is no effect of inductance. Right now, you can see if I remove this one, you can see if I remove this particular terminal, you can see there is effect. And now you can see, right? So there is a peak in the voltages, right? So this peak you can observe, right? And even you can vary that area. I can see now. So it is a different values of firing angle alpha, right? So this is regarding AC voltage controller. You can get any amount of voltage across the load just by varying the firing angle to the thyristors which are connected in anti-parallel, right? So now you can see one cycle, right? Okay, so forget about these connections. So we'll see these connections while you come to the college, right? And you can also, you have to see the theoretical and practical values. So theoretical value you can easily calculate with the help of this formula, right? I have given here Vrms for R load, it is Vm by under root 2 pi, under root pi minus alpha plus 1 by 2 sine alpha. So you can see your seniors have conducted this test at different values of firing angle alpha 0, 30, 60, 90, 120, 150. You can see the theoretical values here, right? Even you can see the practical values. Both are approximately equal, right? And due to presence of the semiconductor materials, semiconductor devices, the practical value you will get it. The practical value is always less than the theoretical values. In case of theoretical values, we assume that the devices are ideal one. There are no drop across them, right? But in practical, you need to consider the drop across the devices, right? Similarly, you can calculate theoretical values in case of RL load, and this expression, it is Vm by under root 2 pi under root beta minus alpha plus 1 by 2 sine 2 alpha minus sine 2 beta, where beta is the extinction angle, and we got it as almost 216 degrees, right? So sorry, here the beta is always constant. You won't get variation in the beta, right? And the beta values depends upon the value of inductor. So since the inductance value is constant, we'll get always the beta value is always constant. Like that, you can correlate the practical value with your theoretical value. Even if you do the simulation, you have to get the theoretical value same as the simulated value, right? Your simulated value will be in between the theoretical values and practical values. If you are aware of the simulation, then you can simulate the AC voltage controller and you can cross check, right? Thank you. Thank you all.